Okay, Organic Chemistry 2342. Here we're going to do Chapter 21, an introduction to cross-coupling reactions that are catalyzed by uh, transition metals. A lot of Nobel Prizes have been awarded for this kind of chemistry, and one of the great things about this type of chemistry is the specificity and the selectivity of these things, plus the very high yields we get from them because of the system we're using. Okay. So we've already introduced organometallics before when we talked about Grignard reagents, okay? And in the case of the Grignard reagent, the metal carries most of the positive charge and the carbon carries most of the negative charge, giving us a very polar bond. We saw this in lithium reagents, we saw this in Grignard reagents, and we saw it in a lithium copper complex, okay? But those are the most common for the organometallics, but that doesn't mean they're the only ones. We can use less electropositive metals like tin, zinc, thallium, aluminum, titanium, and mercury even to do these type of reactions, okay? So the key here is that the more polar the bond is, the more reactive that bond is. The less polar that bond is, the less reactive it is. And of the systems we know right now, the organolithium reagents are most reactive, followed by the Grignard reagents, followed by the organocuprate reagents. Okay. Notice we make most of these organometallic reagents from the organolithium reagent. Okay, so again, let's look at the lithium and magnesium reactions. In the lithium and magnesium, they are the most electropositive metals that we'll use in these organometallic reagents, and therefore it creates a very polar bond. The bond between the copper and the carbon is less polar and therefore is less reactive. But in all of these reagents, the metal acts as the partially positive charge and the carbon acts as the partially negative charge, or specifically as a carbanion, which makes it a base as well as a nucleophile. Okay. So as we know before, that we make most of the lithium reagents or magnesium reagents by doing a dissolving metal reduction. And in this case here, for example, we would make an organolithium reaction by taking an alkyl halide and reacting it with 2 equivalents of lithium metal. And then it it converts from lithium zero to lithium plus, giving us our lithium carbon bond and our lithium halide bond. The same thing happens in magnesium as well. We start with a magnesium 0, and it ends up being a magnesium plus 2, okay? Now, most of the time, when we make the cuprate salts, we make it from the lithium salt, and so we did a dialkyl cuprate, which again, the copper starts out as the copper plus 1, and therefore has to be counterbalanced by the lithium cation to give us our intermediate species. Okay. Please note that because of the electronegativity of carbon compared with that of the metals, that these are fairly polar bonds. As we get to less of a difference in electronegativity between the carbon and the metal or semi-metal, we get less polar bonds. So for example, between carbon and boron, it's less polar bond, or between carbon and tin. Okay, so how do we make these other organometallics other than the lithium and magnesium reagents? Well, most of the time we make them from lithium reagents. For example, to make these aerial boranes, we use a lithium reagent of some of benzene derivative, and then we react it with trimethyl borate. What that does is the anion will come in here, bond to the boron, kicking out an alkoxide, which is then counterbalanced with the lithium metal. So we end up with a lithium alkoxide and our aerial borane compound. So that's a carbon-boron bond is the borane. Okay. We can also do this with other semi-metals like tin. And in this case, we again take an alkyl halide. And in this case, we take a tin chloride bond We displace that chloride and add that carbon-tin bond, plus we end up with the lithium halide as our product here. So again, we go from the more reactive carbon metal bond to the less reactive carbon metal bond. When we get to this less reactive carbon metal bond, less reactivity gives us more specificity in our reaction. Okay, so we know a lot about Grignard reactions. We know we can react them with aldehydes and ketones to make alcohols. Two equivalents of Grignards will give us esters. On esters will give us alcohols. We can do attacks on epoxies, take nitriles down to ketones, react with water to generate alkanes, and actually deprotonate alkynes because of their basicity. Okay, so in all of these reactions, we end up forming carbon-carbon bonds, and that's the key. Before we had the Grignard reagents, the only way to make a carbon-carbon bond was to do SN2 reactions using a nitrile or an acetylide ion. But with these organometallic reagents, we can make a wide variety of carbon-carbon double bonds, and it really is only limited by the types of groups you have. So the general reaction tends to be any organohalide compound and any organometal compound can be cross-coupled to give us a new carbon-carbon bond. And the hybridization on the carbon depends on the different type of reaction we use. For example, if we have a Heck reaction, that's where we can take an allyl halide or a vinyl halide and a vinyl group, displace a hydrogen off that vinyl group to create a new carbon-carbon bond. In the Suzuki reaction, we have some alkyl or aryl halide with a boron compound. In a Stille, we have a halide with a tin compound. In a Sonogashira, we have an acetylide hydrogen being displaced by an alkyl halide. In the Corey House, we use that copper lithium compound. In a metathesis reaction, we actually end up exchanging two of the CH2 groups on two different alkenes to generate a new carbon-carbon bond. Okay, so that means that since we can do this with organometallics and get specificity, we can use SP, SP2, or SP3 hybridized carbons. We typically use something that's a very good leaving group. Almost always it's a halide, but not necessarily. We can use a wide variety of metals to get specificity. We can use magnesium, lithium, zinc, boron, tin, silicon. We can use a wide variety of things as that metal leaving group. Most of the time we use a transition metal catalyst like platinum or nickel. And they are typically named for the inventor because they go through a wide variety of different iterations to get this found, and therefore they publish significantly in that, and they're typically called for those people who created them. But most of them undergo the same mechanism of the reaction. And that mechanism is this cyclic catalytic cycle right here. So the first thing you have is you have a metal. And this metal tends to be in a low oxidation state. It's either a metal 0 or a metal +2. And then when it reacts in its first step with the organohalide compound, it does an oxidative addition such that the oxidation state of the metal changes from, for example, palladium 0 to palladium +2. Once it transitions from that palladium 0 to palladium +2, we now can have that metal is a +2 and our counterbalance is the carbon anion and the halide anion. So we've now counterbalanced that to give us our new carbon metal bond and halide metal bond. Notice that in all cases here, we have what are called ligands. Okay, ligand is a group that donates electrons to the metal before it transitions from a neutral or a low oxidation state to a higher oxidation state. You can think of it as it's just solvating that metal such that we can do that oxidative addition in that first step. Now that we've changed that oxidation state of the metal from like 0 to +2, we can now exchange the halide off of the metal with another metal halide. For example, our magnesium chloride from a Grignard reagent or a lithium, we can exchange that. And that'll give us our metal halide reaction in what we call our transmetallation step. So the transition metal catalyst is now the metal bonded to the more reactive metal substrate on our reagent here. Once we've done that, now we still have our metal at our same oxidation state. In this case, we went from palladium 0 to palladium +2, and it's still +2 here, which means this carbon has a negative charge on it, and this carbon has a negative charge on it. Okay, so we have to get rid of 2 electrons between those 2 carbons to form a new sigma bond. And so we do what we call a reductive elimination. 2 of these electrons go to the metal, so our +2 goes to 0. And 2 of these electrons go to form a new sigma bond between those 2 carbon atoms. Okay. When we do that, we generate our metal 0 again, and this is our metal +2, this is our metal +2, going back to our metal 0. And this goes back again and again and again. And this cycle can happen thousands, sometimes millions of times. And it's very specific because our oxidative addition has to happen first, our transmetallation happens second, and then our reductive elimination happens third. So we always have selectivity between our halide and our metallizing agent will always couple in that exact way, forming our sigma bond.